Let's have one more example. Sample problem 2. A string is tied to box A and passed over a frictionless pulley. Box B is attached to the other end of the string. So again, you have a frictionless pulley. You have a system that is similar to the previous sample problem. But this time, not only is the mass of box A given, 2.5 kilograms, mass of box B is also given, 3 kilograms. And you are asked to determine the acceleration of the system. So this time, the system is accelerating as opposed to the previous sample problem, the system was in equilibrium state. If the coefficient of kinetic friction between box A and box B, box and the tabletop rather, so box A and the tabletop is 0.6, determine the acceleration of the system. So we know mass A, 2.5 kilograms. Knowing mass A, we are able to get weight A, magnitude. We know MB, mass of box B, 3 kilograms. Knowing MB, we are able to calculate the weight magnitude of box B. Coefficient of kinetic friction between box A and the tabletop, so mu K is equal to 0.6. So we pretty much do the same steps, go over the same steps that we did in the previous sample problem. Identify, once you have a drawing of the system, identify the forces present in the system. So again, the objects have mass, so they have weight. You have weight A and weight B vertically downward. A is pressing into the tabletop, therefore, you have normal force N. Because of weight B, B is pulling at the string, producing tension. The string will pull B with tension T, and A also with tension T. The string will pull at its endpoints with tension T. So again, tension is a pulling force. So looking at the orientation and position of the string, you have an idea of the direction of tension. And because of tension, A is being pulled to the right, friction will oppose that. You have kinetic friction heading to the left. Now, the system is in motion. It is accelerating. There's only one possible direction for the system to move. Box B will move down, and because they are tied together, box A will move to the right. So, if there is any acceleration, in all likelihood, the acceleration will be heading in the direction of the motion of the system. So, box A will move to the right, the acceleration is to the right. Box B is moving down, so the acceleration is downward. The two objects are tied together, so that means they will accelerate as one. So there's only one value of the acceleration, even though there are two possible directions for the acceleration. So determine the magnitude of that acceleration. Now here we assume the direction of the acceleration. Since there are only two possible directions for the acceleration, okay? For example, box A, two possible motions of A is to the right and to the left. So if there is acceleration, acceleration might head to the right or might head to the left. If we assume the acceleration to be heading to the right, and that assumption turned out to be wrong, that means the acceleration was heading to the left. The value that you will get for the acceleration will be negative, implying that the direction was wrong. So there's no problem in assuming the direction of the acceleration. Because if we got it wrong, our calculation will give us negative value for the magnitude of the acceleration, telling us we did the assumption wrong. The acceleration was supposed to be heading in the opposite direction. Okay, so for now, let's assume that this is the direction of the acceleration of the system, to the right and then downward. We have identified the forces present in the system. You have two free body diagrams, one for box A and one for box B. Analyze the free body diagrams. There's acceleration in the system, so we equate F net to ma. The system is accelerating. Case in point, let's look at free body diagram 1, box A. So F net is equal to the summation of the forces acting on the system. You have weight, normal force, friction, tension. So sum of all those forces. You have net force. The object A has acceleration. So F net is equal to ma. Since we're talking about object A, we use mass A. Analyze using component method. X component tells us X component of F net X. X component of acceleration, horizontal, positive direction. X component of weight is vertical, so no X component. The same goes for normal force, vertical, no X component. Friction is heading in the negative direction. So this should be Fk because we're talking about kinetic friction. So this is not Fs but Fk. So Fk is horizontal, heading in the negative direction. So negative Fk. Tension is horizontal, heading in the positive direction. Mali ito. This is wrong. This is not equal to 0. This should be equal to ma. Okay? So, correction. This should be Fk, not Fs. And this is not equal to 0. So, consider this to be erased. Because this equation should be equal to ma. Okay? So, please take note of that correction. Isolate tension, we have T is equal to ma plus Fk. We know the magnitude of kinetic friction to be mu k n. So, T is equal to maa plus mu k n. Let's take a look now at free body diagram. First we have the y component. Sorry about that. We are just at the x component, so let's look now at the y component. Y component of F net is F net y. Y component of the acceleration. Acceleration is horizontal. Therefore, no y component. Y component of weight is vertically downwards. Y component of n is vertically upwards, positive direction, whereas Fk and tension are horizontal, no y component. So, plus 0, weight is negative direction, normal force is positive direction. The y component tells us that the normal force magnitude is just equal to weight A. Next, we have free body diagram 2. F net is equal to mass times acceleration is equal to summation of the forces present in the system. So you have weight B plus tension. If you look at the free body diagram, all the vectors involved are vertical, so no y component, no x component rather. All of them are in the y component. Y component of F net is F net y. Y component of acceleration is vertical, negative direction. So, negative MBA. Weight is negative direction. Tension is positive direction. Isolating tension, we have T is equal to weight B minus MBA. Now, we have an equation for tension which we got from free body diagram 1. So, equation for tension, we can equate the two equations which will give us MAA plus mu Kn is equal to weight B minus MBA. Normal force N is just equal to weight A. So, replace N by weight A. The only unknown is acceleration A. We know MA. We know weight A because we know MA. We know MB, so we know weight B. And mu K is also given. So, the only unknown is A. Isolate A and plot in the values, and you'll be able to calculate the acceleration to be 2.673 meters per second squared. Now, our derivation has resulted in positive acceleration, which means the assumption that we made for the direction of the acceleration was correct. Now, if this turned out to be negative instead of positive 2.673, what we got was negative 2.673. That means the direction we assumed was wrong. Instead of acceleration heading to the right and then downwards, acceleration will be heading upwards and then to the left. But since we got a positive answer in our derivation, the acceleration direction that we assumed was correct. And that's it for now. In the next video, we'll finish up our discussion of force and motion with a couple of more examples. So again, that's it for now. Thank you for watching.